Hi, everyone. Thank you again for joining us for PCIe Technology and Automotive Applications, the first webinar in the PCI SIG Educational Automotive Webinar Series. We'll go ahead and get started now. So first off, I wanted to take a moment here to introduce our speakers. We have Ron DiGiuseppe, who is an Automotive IP Segment Manager at Synopsys, Anwar Sadat, who is a Product Definer at Texas Instruments, and then Ido Cohen, who is the Director of Strategic Innovation at Valens Semiconductor. And at this point, I'll go ahead and pass it off to Ron. As a reminder to folks, if you do have any questions throughout the presentation, please feel free to submit those in the question chat box below.
Well, hello, everyone. Thank you, Megan. This is Ron DiGiuseppe. As she mentioned, I'm from Synopsys, PCI SIG member. Today, my colleagues and I will be introducing and reviewing many of the technologies required for automotive electronics, automotive semiconductors that use PCI Express technology. I'll start with just going over some of the trends and use cases of PCI Express in automotive, and then I'll be handing off to my colleagues, Anwar and Ido from Valens and Texas Instruments, to talk about some specific use cases where we finally summarize and answer any open questions. So let's get started. I'll start by just talking about some of the high-level trends affecting automotive semiconductor SoCs. Part of that starts with the amount of change that's occurring in the automotive electronic architectures and how those change is affecting the automotive SoCs. And a lot of that change in the semiconductor SoCs are driven by the applications that are occurring in the automotive, such as those new applications that ADAS and connected car and V2X, plus the architecture transition of the more historic distributed ECUs and the transition to more application domains. And here in the graphic, you can see 5 specific application domains with the gateway application. And feeding those different processing modules for those different domains are the different types of sensors and different types of data that is used by those applications. And just for example, for ADAS, advanced driving assistance systems, those new sensors include things like 3D radar, motion radar, 4D imaging radar, how to process all the amount of data from LiDAR point clouds, as well as the significant amount of data coming from high-resolution image sensors. All that data feeding into ADAS is driving the need for much higher performance semiconductor SoCs. And if you add on top of that the additional requirement of system level and SoC level security based on the many different security vulnerabilities of a modern connected car, the new requirements of functional safety for all these applications that may be safety critical, you can see that the automotive semiconductors are undergoing a need for much higher performance, and that's driving those semiconductors into the more advanced FinFet class processing nodes, which are needed to process all that data. In addition to the advanced applications that we're talking about and new applications, we can see that those applications are being implemented with a high amount of AI. Those new AI algorithms, such as deep learning, convolutional neural networks, are requiring the semiconductor SoCs to, once again, have much higher performance. And we can see in this graph that AI is, of course, in the ADAS application. It's widely been used in ADAS for a long time, but we're seeing AI, deep learning, neural networks being used in powertrain applications, for example, for usage such as predictive analytics, so you can replace the hardware sensors with an AI algorithm monitoring the powertrain, or for example, controlling the electric vehicles. For ADAS, AI deep learning has been used for many of the embedded vision applications, for example, like automatic emergency braking or lane keep aid, all the processing to process those different radar and LiDAR sensors. And of course, AI is used for driver monitoring systems, for driver drowsiness detection, heads-up displays, so that kind of new emergence of AI in those semiconductor automotive applications are once again driving the domain processing modules, the domain controllers, to require more higher performance processing, driving implementation to those advanced FinFet class SoCs. And just as an example, we can see a production ADAS SoC, the public Tesla FSD module operates at 140 teraops, and that's been public for a while, and we can see the AI performance requirements driving up those processing performance in the automotive systems. Then when you kind of drill down a little bit more and you take a look at the sensors feeding those application domains, just another bit of public data was the fact that Waymo uses 29 cameras, and you can just imagine the amount of data that 29 high-resolution cameras drives onto the automotive network. We can see an estimate that some automotive networks are going beyond 10 gigabit, beyond 15 gigabit. So that just shows you the amount of data that those processing domain modules need to process. And then when you throw on that, you add to it the requirements for real-time updates, such as using over-the-air software management, the complexity of the implementation of these SoCs, including the requirement to do over-the-air software updates, is increasing. And then, like I said, adding the increased need for device and system-level security is just overlaying additional requirements onto the semiconductor processors and semiconductor devices, SoCs, in an automotive system. And then finally, looking at the trends that are affecting automotive semiconductors, we can, I mentioned how the distributed ECUs in kind of the legacy cars are now moving to more domain-specific architectures that we mentioned, typically 5 domains such as infotainment, powertrain, ADAS, connectivity. Those implementations are being created in, as I said, 16 nanometer, 14 nanometer FinFet class devices, 7 nanometer FinFet. But in addition to everything we mentioned, there's another trend in the automotive industry that's re-architecting the electronic architecture. This new zonal architecture where, in addition, separate from application domains, the automotive network is being implemented in a more zonal architecture with a different zonal gateway, zonal controllers feeding a central processing compute engine, maybe with an additional telematics control unit, but based on a centralized network. That re-architecting the automotive network, in addition to the higher demands of the applications, are even further driving significant change in the automotive electronics. And I might just paraphrase Mary Barra, the CEO of GM, who very famously mentioned a few years ago that the amount of change in automotive in the current 5-year span exceeds the amount of change in the last 50. And we're seeing that change being reflected in the automotive electronics, especially the semiconductors that implement those applications where PCI Express is mission critical for such applications. And what I'm showing here is just a generic kind of block diagram for an ADAS class SoC. It's a single SoC, but we can see from implementation that a lot of these ADAS modules have multiple SoCs in them, and absolutely showcases the need for PCI Express in these advanced automotive SoCs. And just kind of looking at this ADAS generic block diagram, we see a multi-core 64-bit processors, maybe up to 8 processors, could be up to 12 processors, so heterogeneous processing, very high demand for off-chip DRAM, typically using some sort of LPDDR technology, such as automotive-grade LPDDR5 or LPDDR4, some sort of a AI acceleration subsystem. I'm showing here, because ADAS, it would possibly be an embedded vision subsystem with an image ISP and a DSP graphics controller with typically maybe a MIPI native interface for the vision data from the MIPI-based sensors, and lots of other automotive interfaces. There's typically some off-chip storage, SSD-based storage. All the car makers are moving away from spinning hard drive-based storage technologies. And of course, PCI Express for the connecting multiple chips, either for a chip-to-chip configuration or chip-to-module, and processing all this data, including functional safety to manage the safety for the SoC level that feeds into the safety management at the system level. Just shows you that these automotive SoCs, which absolutely requires PCI Express, is leading the technology for automotive. And today we're going to look at further detail of some of the actual application use cases of PCI Express for the different implementations. And today, my colleagues and I will be going over 4 different use cases. These are just 4 of the typical use cases where PCI Express is mission critical, as I mentioned. And then we'll wrap up the webinar with a summary. So we're going to start with the modular compute processing engine, such as for an ADAS or a zonal centralized controller. We'll also talk about long-reach data backbone using PCI Express. As I mentioned, would be very valuable in a zonal architecture. I will be talking a little bit about PCI Express storage, different types of storage applications, either black box or for infotainment. And then Ido will finalize with a review of PCI Express for telematic control units. So with that introduction, I just wanted to talk about the first application of PCI Express, and for that, my colleague Anwar from TI will talk about the technology benefits that PCI Express brings to automotive. So Anwar?
Thank you, Ron. My name is Anwar Sadat. Hello, everyone, and I'm from Texas Instruments. So we'll talk about the PCI Express technology benefits. So high bandwidth is probably the most important benefit of PCI Express technology. The bandwidth of the technology doubled in each generation, starting from Gen 1 to all the way to currently defined Gen 6. The bandwidth doubled. And PCI Express in general kept up with the industry need. So as you can see on the graph, that the blue graph shows the I/O bandwidth need from enterprise server, and the purple, probably the color, that shows the PCI Express generation speed, the raw speed. So PCI Express was able to keep up with the technology, the industry need. So another advantage of PCI Express is its flexible link width that allow scalability. So PCI Express can be bifurcated into by 1 or can be used as by 1, by 2, all the way to by 16. So that is key for applications where the scalability is important, the amount of data throughput that you need, whether it's in between two modules or within a module, multiple processors, that flexibility or scale, probably is key. PCI Express is backward compatible. So if you implement in Gen 5, it can work all the way to Gen 1, for example. So one key benefit of PCI Express that can be critical in automotive applications, it's ultra low latency and reliability. So the interface has less protocol overhead and guaranteed reliable transport on hardware level. So no software overhead needed, and it makes the interface to be efficient. The applications where real-time need dictates short latency, PCI Express works well. PCI Express inherently, since it's a hardware-driven link, provides a lot lower latency compared to other comparable technologies that can be considered in automotive applications. So many links require low latency for quick response time, as well as efficient data throughput. So if the overhead actually reduces your overall pipe bandwidth, that's probably can be a significant disadvantage. And PCI Express offers a very high efficient data pipe, whether it is in between processors or for long haul data transport. That is a very positive trait to have as a technology. So PCI Express latency in general in the range of 1 to 100 nanosecond. Addition of PCI Express technology benefits. DMA addressing. The interface has built-in DMA method that does not require packetization. The DMA allows the processors to access shared memory that makes the implementation more efficient, lower cost. Another benefit of PCI Express is automotive functional safety. It has CRC, advanced error reporting structure built into the transaction and application layer. It has message counter. So the PCI Express interface is robust enough that if a packet is received at PCI Express boundary, it is guaranteed to reach the destination without an error. One of the big benefits of PCI Express as a technology is its breadth in the ecosystem. It's an ubiquitous interface, a very pervasive across the industry. Almost every processor, SoC, FPGAs has PCI Express already built in. It has a very large software base, and for a new platform development, software always plays a big role, and having that software base always makes the implementation of that platform easier and lower cost. And flexible interoperability with off-the-shelf components and cables, also another advantage. A quick prototype is possible with industrial components. So let's look at some of the use cases that Ron was introducing. So first use case is compute scalability, where you have a ECU or cluster of functions, in a zone or in a physical location, and the amount of compute we need depends on what we are trying to do. Some of those applications of this scalability includes autonomous vehicles, advanced driver assist systems, ADAS, infotainment, and some of the trend we are seeing is the processor's accelerator GPU connectivity that is scalable. In general, we are seeing number of sensors are increasing, in some cases exploding. Compute processing needs are increasing. The number of teraops that a car needs to handle today is very wide-ranging. A number here is 30 to 700 plus, but the point is that, depending on what that car needs to do, the teraops can vary quite a bit and can be as high as 700 teraops. So where do you see this, the compute scalability today? So today we do see the ADAS domain controllers use this part of their platform implementation. And when domain or zonal architectures are implemented, we also see the scalability, the use of scalability in the platforms. So what are the typical technology requirements for these applications? High bandwidth, scalability, low latency, hypervisor, visual applications, better usage of power, thermal, functional safety, security. So on the right, we see a couple of block diagrams. One shows that as domain controller with accelerators connecting to the automotive processor SoC or a centralized unit with number of accelerators depending on the platform. So number of sensors, which features are enabled, dictate the compute power, autonomy depth, and ADAS implementation may dictate number of add-on accelerator platform may need. So on the bottom, as we can see, another example of infotainment controller, where a processor is connected to some accelerators and some GPUs. So in general, number of displays, the choice of external content, whether there are external connectors that user will or passenger will feed in video content from outside. The video resolutions are among few variables that determine how much data and the number of GPU we need to handle a specific platform need. So PCI Express in general, scalable interface with data rate and bus width flexibility. The need for data and compute scalability from vehicle platform to vehicle platform suits very well for PCI Express technology. For autonomous vehicles, the level of autonomy dictates data throughput and processing needs in general. So next use case we are looking at is data backbone applications. And application could include ECU processing redundancies, sensor fusion and aggregation, ECU zone ring architecture data transfer. Some of the trends that we see, the high bandwidth between zonal ECUs, the data rate in previous platforms was in the range of megabit per second. What we see today, gigabit per second. But with the advent of so much data processing and sensors in a car and video content and user experience, number of the data, the bandwidth requirement can top 5 to 40 gigabit for a link. What is the general technology requirement for this use case? High bandwidth and low latency, EMC, EMI reliability for long reach cable link, automotive functional safety, security, and quality of service. So on the right, we are seeing that block diagram where we talked about zonal architecture, where each zone is physically located in some portion of the car and handling all the sensors and actuators and all the functions, do some processing, and the different zonal gateways are connected to each other. They're also connected to the CPU or central processing unit or a cluster of CPUs there. So the compute network in cars with full autonomous capability is fast approaching to the level of a supercomputer. So data from radar, LiDAR, camera, ultrasound aggregated, and fused for decision making. So the data backbone carries processed and raw data to centralized compute unit, and functional safety and reliability also dictates redundancy into the data network. The data backbone, PCI Express is well suited to provide a efficient and reliable link or a method of data transport. So we are seeing some actually traction for PCI Express in these kind of applications, in data backbone applications. We have seen some implementation of PCI Express Gen 3, where some testing of EMC/EMI, also some encouraging news. Cable vendors are coming forward, developing better cables, more reliable cables, and that can provide higher data rates. So let's go to the next use case that Ron will present. Ron?
Thanks, Anwar. This is Ron DiGiuseppe from Synopsys again. I'll go through use case number 3, which is looking at storage in the car as PCI Express-based storage. And typically, there's maybe 3 primary areas in the car where storage is necessary. One is in black box recorders. We can see a statement here that 100% of new cars have event data recorders. Typically, they were using a small amount of memory because it's required that 30 seconds of the previous driving of video and sensor data be recorded. But we're seeing OEMs, especially the autonomous vehicles, recording, and in commercial vehicles as well, recording all of the sensor and data as the car proceeds. So the amount of storage is for black box recorders is growing significantly. And we also see the need for self-driving cars, autonomous vehicles, that real-time location is 100% required. And one of the ways to do that is have real-time updates to the maps. So that requires a significant amount of storage for generally the ADAS domain controller or a self-driving car, as well as the amount of storage in just the infotainment applications. We can see new driver cluster monitors going as large as 42 inches, so a significant amount of storage for those infotainment and the central processing, as Anwar mentioned, about zonal controllers and central domain processing. So with those applications, storage has specific requirements in terms of automotive, one being very high endurance. Those storage, SSD-based storage, have to have many write cycles over many years, so extended data temperature at the high automotive temperatures are required for that 15-year operation lifetime. Very high density, depending on the application, could be as much as a terabyte. Very low latency, so PCI Express storage with low latency, especially using an NVMe type implementation, is the absolute required to get the lowest latency. And that high bandwidth and very fast startup and boot time. These are all critical requirements for storage in these applications. As I mentioned, they have to operate at high automotive temperatures with different mission profiles at different ambient and junction temperatures, and be very stable over time. And with the amount of virtualization occurring, especially in these central processing modules, so SRIOV is very applicable for the virtualized applications. So with these requirements in terms of PCI Express-based storage, we can kind of look at what the options are. Traditionally, there's been like a lot of the mobile type storage applications, interfaces like eMMC or UFS have been used in automotive storage, but we're seeing now a transition to PCI Express-based SSDs, especially NVMe oriented SSDs. Especially because, as I mentioned earlier, that spinning hard disk-based storage is typically not preferred by automotive just due to the amount of vibrations and the long-term reliability that PCI Express-based SSDs can provide. And PCI Express-based technology has, based on the PCI SIG, added specific features and functionality that helps PCI Express-based SSD storage, especially with NVMe. Those RAS features that Anwar mentioned that are useful for automotive channels are absolutely useful in these storage applications such as CRC and the ACNAC operation. So to ensure that data is correct, having timeouts that may then ensure that there isn't any data being dropped. That end-to-end CRC is also useful for functional safety to make sure that data integrity. PCI Express, especially because the centralized processing, even with high performance FinFet based technology, it can have very high power, and that high power is difficult in a car to eliminate the heat. We're seeing a lot of demands for low power operations. So the fact that PCI Express has L1 substates for low power operation is very important in these high performance applications to minimize power, specifically to minimize the amount of heat. And then we see that the PCI SIG for the PCI Express standard has implemented a number of ECNs to enable storage, really provides PCI Express the ideal technology for these high performance storage applications in the automotive. Things like the removal of the requirements for a host bus adapter isolation for PCI Express root complex to access the storage, and the implementation of separate ref clocks for independent SSC. So these features in the PCI Express spec just enables PCI Express to be really the correct technology for kind of high density SSD based storage for automotive. And with that, I'll hand it over to the last use case, which my colleague Ido will present.
Hi, thank you, Ron. Hi, everybody. I'm Ido. I'm from Vela Semiconductors. And I'll try to go over the last use case of the telematics connectivity unit and the ability or the advantages of PCIe with that. So if you look at the typical TCU and going forward, there are multiple connectivity chipset there. Either it's an LTE or 5G modem. And as we progress with time, it will be higher bandwidth coming with the 5G implementation. We have the Wi-Fi, Bluetooth, GNSS modules that are used both internally and sometimes also externally. And of course, the V2X, which is getting traction and also getting into more and more vehicles and will be widely spread in the future. So we have a multiple units mostly located at the same place, usually at the rooftop as shown here as in the example, and they need to connect to usually to the head unit. And most of them, the native interface are PCI, and the ability of the PCI to bring the flexibility of the interface, allowing to support easily higher bandwidth without major changes to the architecture or to the devices is very important here. So as we see the bandwidth growing more and more, we have as part of the PCI SIG already capability to support this kind of high speeds inherently with the next generations, which are, as mentioned previously, backward and forward compatible, so no major integration topics while doing that. Also, having most of these devices already natively connected, natively interfaced with PCIe can simplify possible future integrated architectures for such devices. So that's another trend that is seen and can be accommodated very nicely with PCI. So looking at the requirements of such devices, so the scalable or scalability for multi-gig throughput is very important, as these devices grow very fast in throughput. Also, the security is very important, especially for items like V2X that will require security and functional safety to maintain the integrity and authentication of this data, which is highly important. Again, in addition, the data reliability and integrity that is required for such devices is very important, and is also a very good match to the capabilities of the PCIe. And of course, there is the need for the EMC-AMI reliability of long-reach cable link, which, as already mentioned previously, there are already some examples of this being able to withstand the harsh environment of an automotive. And this is very important going forward, that PCI can be transmitted over a long-reach cable and maintain the native interfaces without the need to go through any translation. So this is the use case 4 that we wanted to present, and I'll go forward to the summary and try to wrap everything together based on what my colleagues and I try to share here. So in general, PCI is a standardization organization. The PCI SIG provides a standardized solution, which is the preferable to the automotive market. It is preferable because automotive market requires clear roadmap for long term, as the economy of scale is driven by multiple players, and the assurance of long-term availability and interoperability that is very, very important in an automotive market. And this is all covered or being produced by the PCI. The certification and qualification process in automotive is stricter and much more harsh than the commercial markets. There are longer processes, harder environmental requirements as temperature and vibration, and there is also harsh EMC and DMI environment. So it's important that this type of requirements will be met and could be tested and qualified in a good manner. In addition, of course, automotive, the security and functional safety end-to-end solution is very important in order to be able to support the automotive market and to maintain the vehicle safety during the lifetime of the vehicle. The last thing that is really important in the requirements is that to have the backward and forward compatibility. This is something that for products that will require to be 10 and above years in the market, it is very important to be able to support it and to be able to support upgrading some of the components and still have backward compatibility. So, for example, a base or CPU unit, ECU, main ECU can stay as for the whole lifetime of the vehicle, but some of the peripherals could be upgraded and still do not have any integration and compatibility issues. So the easy migration and upgrades is also very important, looking at a lifetime of a vehicle, which is more than 10 years. So looking at these requirements, we think that the PCI architecture has a well-established ecosystem with strong technical leadership that can support these kind of requirements. It is optimal for closed, highly integrated systems with limited scale, which a vehicle is actually a big box that is closed. You do not want anyone to plug and play or replace items without any main unit acknowledgement, or to be putting replacement parts that are not authorized. So it's important to keep this closed system, and PCIe system is very well accommodated to that. The low latency and the fast and flexible power efficiency of the PHY is very important also to maintain the power requirements and the high speed and low latency requirements. The PCI is hardware-focused protocol with low overhead and direct memory access, which also is very important. The end-to-end reliability and security, which the PCI provides, is also matching and important for the automotive requirements. And the technology is flexible and scalable and allow the increase of bandwidth with no major architecture changes, and for products that will require to be available for a long time, this is very important. As a major standardization body, PCI provide also large software base supporting developer community and the compliance program to ensure the interoperability, which is very important for the overall market. So just to finish up, please remember, it's always important. We have a lot of, as designers, we always have a lot of tools available to us. And it's always important to use the right tool for the right way, in the right way. And we think that in many cases, PCI is the right tool for most of the use cases that we presented. And I think we are now in the session of the Q&A. So Megan? Am I audible?
Yes, hi. We've gotten a few technical questions from the audience. Yes, Edo, we can all hear you. And Megan will be asking the panel a couple of these questions. I think one of the questions, first one was, which generation PCI Express technology will be used in automotive applications? I can answer that, but also like to get contributions from both Anwar and Edo. Since Synopsys provides intellectual property IP cores, and we're the leader in interfaces, we see a lot of different SoCs being planned in the industry. And for automotive SoCs, we see a lot of adoption of PCI Express Gen 3. But for the kind of ADAS and higher end SoCs, I'm seeing PCI Express Gen 4 being the predominant PCI Express generation flavor that's used. And Warito, feel free to comment as well as which PCI Express technology is most widely used for automotive.
So Ron, thank you. I think we see the same trend from Texas Instrument point of view. PCI Express Gen 3 for some long-haul engagements, and PCI Express Gen 4 for ADAS applications. And PCI Express Gen 4 is being implemented in some reference designs and so forth. That probably will come out to market in next few years.
Yes, I agree. I think that from our perspective, Gen 4 is getting traction and more and more visibility, and I think that's a very important use cases that to support the Gen 4.
Thank you. The next question is, will the usage of retimers along with PCIe technology be helpful in automotive applications?
So Anwar, I will take that question. Yes, I think we do see the PCI Express retimers and redrivers can be useful. Retimers, especially for the long haul, to drive longer cable, and redrivers probably more scalable applications. But yes, we do see the use of those signal conditioners that can help in PCI Express in automotive applications.
The next question here is, low power management and PCIe technology useful in automotive applications?
So this is Ido. I'll answer this. Yes, I think low power management is very important, and this is important in general for automotive market, and the abilities that the PCI brings with the low power modes is very important, especially with devices like storage and connectivity, wireless connectivity, which requires to have lower power consumption in order to reduce the heat and maintain the environmental requirements. So yes, low power management is very important.
Next question here, what is the host type that is transmitting the data to the ADAS via PCIe technology?
So what's the host type that is not? So maybe we need some clarification. I'm not sure that we fully understand this.
From my view of this question, I would just say that the ADAS domain controller would be a root complex, and then they would have the host, the application running on that processor, and PCI Express would be used as an expansion bus to some sort of a application acceleration device, like a GPU or an FPGA or just another SoC. So I would say the host type is a root complex, is my thought on this question.
Moving on to the next question here, how can we synchronize different endpoints in the PCIe system? Is there a way that we can control the latency and jitter introduced by PCIe?
So, Anwar, I'll try to answer, and maybe other you can join. So, all these endpoints are being handled right independently. I think PCI Express has that capability inherently, controlling the latency and jitter introduced by PCIe. Again, I mean, jitter is a physical link phenomena, right? And PCI Express has link training to minimize the jitter so that the link is successful. Sometime I think another question was use of redriver retimers. Redriver retimer can be utilized for more challenging electrical links. But PCI Express has established methods and mechanisms and tools to handle these things.
Next question here. In your TCU use case example, you showed the connection between the TCU and the head unit. How long of a cable can, in terms of maximum length, be used in such a use case?
Okay, so this is basically differentiating between, it's different between the different OEM, but I would say that considering at least 7 meters is required as the minimum maximum length that it should be considered for such devices. So.
Great, thank you. And then the next question here is, what is the typical external ref CLK required for PCIe 4.0 and 5.0? Is crystal unit or more complex oscillator preferred? Do you want to skip that one?
Yeah, no.
So yeah, we'll have to probably take that question and come back.
Okay. Last question, is the TCU typically located on the roof? Is the temperature more of a concern at that location?
So from that perspective, if it is located, the location on the roof, yes, it has also a temperature implication, but I think that this is an implementation decision, and specifically not PCIe related advantage or disadvantage. It's more of a implementation decision.
Great.
So Megan,
go ahead.
Megan, I will respond to the previous question, the ref clock question. So, if it is a separate clock, right? PCI Express has the mechanism to forward the clock, and that can be used, or independent clock. And crystal probably would be a preferred method for higher speed data rates.
Great. Well, thank you all so much. At this point, we are out of time to go through the remaining questions, but given the amount of questions we have, we will look at doing some kind of follow-up here. But we did want to thank you all for attending the first entry in the PCI SIG Automotive webinar series. Again, we are looking at doing a series of webinars focused on automotive applications moving forward here. So as a note here, the slides will be available on the PCI SIG website, and then a recording of this will be available on Bright Talks as well as YouTube. Thank you again to the presenters and everybody who was able to attend.
Okay, thank you.
Thank you.
Thank you.